Good evening, Way Happy fans. This is Mr. Meyer from the studios of Way Happy, and we are here to talk about 12.5 mathematical induction at the end. But let's start off with a little bit of infinite geometric sequences or series. Now, a geometric sequence or series we know is something that is got a common ratio. And if that common ratio, if the absolute value, I should say, of that common ratio is less than 1, and the series goes on forever, we call that infinite, we can actually kind of guess where the sum is. Now, we can't really find the sum, but we can get really close to the sum, and actually the numbers get so small that you're adding to the sum that they don't matter, and we call that convergent. We say the series converges on a certain number, and that's like saying it has a sum. If we can't add it up, then it's called diverging. So divergent means that we can't find a sum. The limit also tends to be where that number is headed as we go to the limit of infinity. And then we'll talk about mathematical induction and counterexamples, which are proofs to prove theories or statements. All right, so let's start off with a little infinite geometric series. Here is the formula. If you have a series that goes on forever and ever and ever, common sense would tell you can't add it up. However, you can add it up, or at least find out if it converges, if it's geometric, and if r is less than 1. So a lot of ifs, you notice. Doesn't mean you can always do it. So most of the time you're going to tell me it's a divergent sum, meaning I can't add it up. But in the rare case it's geometric, and in the rare case that geometric series has an r value of less than 1 absolute value, r is less than 1, you'll be able to say, yes, I can sum that up. So here we go. You just do your normal stuff. You got a nice list here. Looks pretty nice. One thing I do like is the numbers are getting smaller as I go on. So that makes me think it's convergent and that I would be able to add it up. But let's find out what they're doing. So first I would check if it's arithmetic, and it looks like, hey, look, they're subtracting 9, then they're subtracting 0.9. Oh, that's not good. It's not arithmetic. Now let's see what the r value is. So if you remember from last video, we take the second term and divide it by the first term, and that works there. Now I'll do it again. Let's see, what is 0.1 over 1? Well, that's the same thing as move the decimal over 1 over 10. Whoa, it's the same. So good news. If you notice the rest of the pattern, it looks like they're always multiplying by 1/10 or dividing by 10 if you like. And they are. And so once you find out what your r value is, you say, hey, is that less than 1? It is. So therefore you call this convergent. And all that means is that we could actually sum it up. In fact, the way you would sum it up is you would do the first term over 1 minus r, see what you get, and that would be your sum. And end of story. But they didn't ask me to find the sum, so I won't do it. Second sequence, look what they did here. They multiplied by 3, and then they multiplied by 3, and then they multiplied. Oh, I like it. It has an r value of 3, but then go up and tell me, can I add that together? Unfortunately, no. The r value is too big, and we call that divergent. Ooh. Right? So now we have divergent and convergent. Convergent means I can add it up. The terms should be getting smaller because they are getting tiny at the end. So way out here at the end of the sequence, they're getting really small, and therefore I can add them up because they don't really matter. These guys keep getting bigger and bigger, so this sum is getting bigger and bigger, and therefore I can't add it up. So kind of use some logic here, and you won't feel too spooked. All right, what about this? Number 3, find the infinite sum if it exists. All right, so it's a sequence that goes on forever and ever and ever, and they want me to add it up, and that's fine. Notice they're not saying sum up the first 5 terms or something. They're saying sum up the entire list. So we just got to figure out what the heck are they doing. Well, it doesn't look like they're adding. It looks like they're multiplying. Looks like they're in fact multiplying by negative 0.2, at least by the first one. But as you see, that carries on to the next one and the next. So therefore, that is the r value. That is a good series. That is convergent because the absolute value of r is less than 1. So here comes my sum. The infinite sum is the first term over 1 minus r, or for us, 1 over 1 minus negative 0.2, or 1 over 1.2, which I could use my calculator to tell me what that is. And that is 0.8333 repeating. And that's what it sums up to. It sums up to almost 1, right? It sums up to 0.83 repeating forever. Nice. What about this next guy? Giving it a little bit of form, and it looks like my computer went a little funny. This should be infinity here, and k equals 1 should be here. So it should look like that. It looks like Word just kind of smushed it together. No big deal. Let me find out what this series looks like. So if I plug in a 1, I get a half to the 0, which is 1. Then if I plug in 2, I get a half to the first, which is a half. If I plug in 3, I get a half squared, which is a fourth, and so on, and so on. And I start to see what it looks like. And yes, it definitely looks like a nice little sum, or sorry, a nice little series. Looks like they're multiplying by a half every time. So I know that r is a half, and in fact, if you know the formula, whatever gets the exponent, that's your r value. And whatever doesn't have it out here, that's your first term. In our case, there's nothing there, so a 1. But shh, we'll pretend we didn't notice all the tricks, right? So we wrote it out, and we figured out that, hey, look, they're multiplying by a half. Therefore, this is convergent. And because it's convergent, I can find the sum. So let's do it. The sum is equal to the first term over 1 minus r, which is the first term over a half, which is, copy dot flip, 1 times 2 over 1. And you get 2. So that actually adds up to 2. Now again, really weird. But try it. If you're bored, take a calculator, start adding those numbers up, and do it for an hour and see what you get. And I guarantee you, you will be near the number 2. You won't be quite there. You'll be like 1.99 whatever. But give it a shot and see what happens, and you'll have a good time. All right, and let's try this next example that says write 0.63 as a fraction. Well, that's a little bit of a typo, because 0.63 as a fraction would be 63 over 100, and that's not nearly as exciting as anything we're doing. So let me kind of get rid of that real quick and say I wanted 0.63 repeating as a fraction. And the cool thing about repeating decimals is the fact that you can use this infinite sum formula, because all this is 0.63 plus 0.0063 plus 0.00063, and notice it's just this infinite sum of 6 threes in our case. So the first term is 0.63, while the r value, what they're multiplying by, is just how many digits you actually have repeating. So for us, it's 1/100th, right? 2 decimals. So 0.01, or some people will write as 1 over 100, that's fine. 3 decimals would be 1 over 1,000, or 0.001. And you use this formula. You're like, s is equal to the first term over 1 minus r. And just be careful, you get 0.63 over 1 minus 0.01, which is 0.63 over 0.99, which is, move the decimal twice, 63 over 99, and then reduce that bad boy. 21, oops, I almost said 31. 21 over 33, which I think that's as far as I can go, and grab my calculator and look, 21 divided by 33 is 0.636363. Woo! Way to go! Crazy cool math. Alright, let's let you do an infinite series problem or two, and I'll see you in a minute. Alright, nice work. Now let's talk about proving something. Or maybe let's talk about disproving something, called a counterexample. Let's just say somebody comes along and tells you that a cubed, or whatever, x cubed, or whatever you want to call it, is always bigger than x squared. Or in this case, I've used a's. So a cubed is always bigger than a squared. And a is a whole number. And you'd say, okay, yeah, that sounds pretty good. 5 cubed is bigger than 5 squared. 6 cubed is bigger than 6 squared. Negative 5 to the third is bigger than... Oh, wait. Is it? Like negative 5 cubed. Oh, they said whole numbers. Oh, can't use whole negatives. No wonder. You're probably right. Yeah, that's probably true, right? Well, if you can come up with one counterexample, you have disproved it. And I almost did, except for they had the caveat we had to use a whole number. And if you don't remember whole numbers, that's 0, 1, 2, 3, 4, 5, all the way to the biggest number you can think of. And so it does hold true for a lot of them. It holds true for everything. And in fact, I can think of only 2 it doesn't hold true for. 0 cubed is not greater than 0 squared. That's not true. And so that's called a counterexample. And likewise, you could have done the same thing for 1 if you wanted. So this is called a counterexample to your claim, or whoever's claim, and that's how I can disprove something. So if someone wants you to find a counterexample, they say, hey, give me an example of where it's not true, and you're done. And you've just disproven somebody's entire theory. You've said, hey, look, you thought that was true. Here's where it's not. Come back with a new theory. And so maybe they'll come back with a cubed is bigger than a squared for all the values of a is bigger than 1. And you'd say, hey, all right, now I'll look to see if there's anything to disprove there. That's a counterexample. I think you used them in geometry, so they probably feel pretty fun. Now another type of proof is called mathematical induction, and mathematical induction has 2 or 3 steps depending on what book you're reading. And here they are. Step 1 says take something you want to prove, like this beautiful statement right here. Somebody says this sequence is created by this formula, and they want me to prove it. Well, the thing is, you got to show 2 things. There's called the base step. That's where you prove it works for n equals 1. And then the weird part, the induction phase of this happens. And what happens here is you then say, all right, let's say then now it works. It worked for 1. Now let's say it works for everyone. And let's then prove it works for the next one. It's kind of like what I read once was the domino effect. If one domino falls and it hits another one, then the next domino will fall and hit the next one, and all the dominoes will eventually fall as long as it's lined up nice and neat. And that's what this is. This is saying, hey, if you prove it for one thing, then prove it for the next one, and then from there on, it'll just keep proving itself all the way along. And I was like, okay. So that's what this does. So let me walk you through an induction, and it's kind of yucky, but it's also kind of fun. So here we go. First, you do step 1, right? And step 1 is show me it works. In other words, show me that it works for just the first value already. So if I do that, I would be saying that show me what 3n minus 2 is equal to n times 3n minus 1 all over 2, that works when n is a 1. So plugging a 1 in, put a little question mark there because we don't know if it's true or not, and I'm going to say 3 times 1 minus 2 is equal to 1 times 3 times 1 minus 1 all over 2. So this is 3 minus 2 equals, now what do you get on this side? You get 3 minus 1 over 2. You get 1 on this side, and you get 2 over 2 on this side, which, hey, that is true. It checks out. So step 1 checks out. You say, hey, look, yep, it worked for the first term, for when n was 1. So now let's just assume it would always work. So step 2 says, all right, from now on, we're going to assume that since it worked for everybody. And instead of calling it n and confusing it, let's call it k. So 1 plus 4 plus 7 plus ... plus 3k minus 2, that is true for everybody. It will equal k times 3k minus 1 all over 2. So that's your induction setup, your induction phase, right? And now what I'm going to do is I'm going to prove that if it worked for that thing, it'll work for the next one. So I'm going to replace all the k's with k plus 1. So I'm going to come down here because I think I'm going to need more room. And in step 3, I'm going to replace all the k's with k plus 1. So you're going to have 1 plus 4 plus 7 plus ... plus 3k minus 2. And now the next number that would be after that would be 3, and then I'm going to sneak a k plus 1 in here, minus a 2. So notice what I did. I took the k out and I put a k plus 1 in its place, and that would equal to, on the right side, change all the k's to k plus 1. So k plus 1 times 3, k plus 1 minus a 1 all over 2. So I'm saying that would work for the next term. If it worked up until the first terms, the first k terms, it would also work for the next one after that. And then you could just say that that would hold true for the rest of the way. Then it would work for the one after that and the one after that. So since it worked for the number 1, it would work for the number 2, it would work for the number 3, and it would just continue to work for every single number after that. So how do we prove it? Well, we got to try to, again, make these two sides equal. Does this left side equal that right side? Well, yeah, maybe. Let's see. One thing I do know is I know what this is right here. I know that this was true up here, right? So I'm going to bring that over. I'm going to take all this junk out, and I'm going to say k times 3k minus 1 all over 2 plus 3k plus 1 minus a 2. Is that equal to this? And now you just find some way to do it, right? So I think I'm going to try to pretty up the left side. So the way I would do it is that's all right. Let's common denominator. So let's get them both a common denominator. I could probably clean this up a little bit. This is like 3k squared minus k over 2 plus, because this is only one fraction on the right side. So let's make this one fraction. What is this? This is 3k plus 3, 3k plus 3 minus a 2. So you guys mind if I combine those and just get 3k plus 1? So 3k plus 1 is that. Now I can't add them together until we multiply this by 2, so multiply top and bottom by 2. And I have 3k squared minus k over 2 plus, what's that, 6k plus 2 over 2? Woohoo! And we can finally add those guys together. So we get 3k squared plus 5k plus 2 all over 2. Does that equal whatever the heck you have on the right side? Well, sure. I could probably factor that apart. How good's your factoring skills? Let's hope they're great. So remember what I do. I multiply the outside numbers is 6, and it's got to add up to 5. And what two numbers is that? Piece of cake, 3 and 2. Now, if you remember that weird bottoms-up technique or whatever you do, you write the split the middle term, do whatever you do. But for me, I divide both of them by that first term, 3. And I get my two answers. My two answers are x plus 3 over 3, which is x plus 1, and x plus 2/3, which I have to bring the bottom up. So 3k plus 2, I was saying x, sorry. So I factor that down to k plus 1 times 3k plus 2 all over 2. And I'm saying, is that the same as the right side? Well, look at what we have. We have the 2 in the denominator, check. We have the k plus 1, check. The only question is, does this highlighted part look like this highlighted part? And I bet if you look at it for a few seconds, you would say, yeah, that's 3k plus 3 minus a 1. That would be 3k plus 2, and that's what it is. So therefore, this checks out. And that is called proving by math induction. We proved it for n equals 1, the first case. Then we proved it for everything after that. And that way it will always be true forever and ever. That is the joy of math induction. Let's do some tomorrow. You have a great night, and I'll see you tomorrow. Stay happy.